Okay, so this lesson is going to be pretty short because this is the third model that we're seeing today, which is called compounded continuously. It is dealing with all the exponential growth and decay models. You saw the first one that dealt with just growing and decaying, increase, decrease, without any kind of compounding rate. Then the second day we saw compounding rates with daily, weekly, monthly, yearly, semi-annually, and so on. And now finally there's this word called these words compounded continuously, and so we have to see how we're going to figure out how much money that would accumulate when an account might be compounding continuously. So there is this irrational number which is called the natural base E, and it is on your calculators. If you check on a scientific or on a graphing calculator, it is written right here on the yellow part, which is it's right under ln. So you can either hit shift and then press ln and you'll see that E show up. It doesn't show it as an exponent, but technically when it does this, it wants you to put in a number for an exponent after it. And so if I did 1, e to the first power, this is the number that E is equivalent to. And this type of number is called irrational because it's just a lot of different decimals, no particular pattern, but it just it goes on forever. Of course, it doesn't fit on the whole screen even. Another irrational number that you probably know more about is pi. So like when I press pi, I know that that's the irrational number that shows up. So we're not working with pi. We are going to work with E in this unit, but we're not going to do too much with it. We could graph with E, we could write equations and so on, but we're going to kind of skip a lot of that. It just talks about here where E comes from, because again, this is what we saw on the calculator. The E was about 2.718, so on. You do not need to memorize that number, but since this is what it's equivalent to, what ends up happening is when you are compounding yearly, semi-annually, quarterly, monthly, weekly, and then daily, as you do that, the number starts to start approaching, if you use this right here, this equation, it starts approaching 2.712 or 82 and so on. So it started approaching E as you get to doing it more and more times rather than just doing it to 365. If you continue compounding almost instantaneously, that's the number it starts approaching. So formulas will now use this letter E to represent continuously. So we can identify from equations whether it's growth or decay like we did before. So like let's start with letter B, for example. When we saw this equation back a couple of days or a week ago, we were able to decide that this was exponential decay. And the reason for that, when you write your explanation, was that A was positive and B was between 0 and 1. But we can only do that explanation when you have an A and a B like this, when you don't have any E's. But if you look at the other three choices, they now all have E's in them. So when you see E as like your B value, technically, right, because they have an A and then E is like your new B value, E tells you then that you need to look at the exponent. If the exponent is positive, then it's growth. If the exponent is negative, it'll be decay. So it's that simple. For this first one, you write down decay, and the reason is because you have a negative exponent. For letter C, another decay because you have a negative exponent. And finally, the last one has a positive exponent because it's just a 1x, so it's growth, and you write positive exponent. So the A value doesn't tell you anything for these three because they're, even if it's a number bigger than 1, like 4, or these decimals or fractions, they just tell you whether it's like a shrink or a stretch for the A value, but does not tell you whether it's going to be growth or decay. So just that exponent, if it's positive or negative, that's how you decide. All right, so we are skipping the graph entirely. We could do a graph like this if you wanted to, but again, with E, you'd need a calculator to help you with the values for E, either a graphing or a scientific calculator to help evaluate each point, and then you would move it. But again, we're not going to do that. You could do your transformations if you wanted to, but that's pretty much it. So if I go to the back, we're going to cross off this one as well, and we're going to go jump right to the formula or the new model that we're looking at, which is for continuously compounded interest. So if you're reading through a scenario saying how much money you start off depositing and how much interest will be compounded, it has to say the word continuously after it says compounded if you're going to use this formula. And so the equation will say A equals, A is still the final amount. So this is your final amount, or like how much money you end up with. P is still your starting amount, or it's like a principal is what we call it. And you can put in parentheses starting amount. R is a rate still, just like it was before, and we still express it as a decimal. That means you have to divide it by 100 if it's written as a percentage. Like 50% rate would mean 0.5, or 5% rate would mean 0.05. And time is still the same as the others as well, where it just represents how long that the interest would be compounding. All right, so let's try a few examples using this equation. Remember, E is a button on the calculator. You really cannot do these without a calculator. A scientific graphing will really help here. So I'll show what I put on the calculator after we set it up. All right, so let's go ahead and start this first one. You deposit $3,000 into an account that pays 3% annual interest. So ignore the word annual here. It's just saying that over a period of a year, they're putting interest in continuously, compounding it continuously, and then what will happen after 10 years. So because it said compounded continuously, you know you have to start with this equation. It's a PE to the RT, or a lot of times it's abbreviated PERT. So we start with A equals 3,000 is what we start with, or principal. Then there's a letter E. The exponent now is 0.03, and the T is 10. So I would put all of that in parentheses, especially if you're using a scientific calculator. This is how you have to type it in. So we start with 3,000. Then you hit Shift and the LN button on the right here, that gets you the E to show up. Now I know it's not showing an exponent key, but because it says E to the X, that's why it's already there. So you just type in 0.03 times 10. If you're using a graphing calculator, you still find the second LN button, and it should sometimes even give you a caret key with it, so you can just put parentheses around this entire thing. But if you don't use parentheses, then technically the whole thing is not an exponent. When you type that in, you should get this large number. It comes out to 4,049 and 58 cents. If you round that up, please be careful with rounding. Look at the second number. It's a 7, and the number right next to that 7 is a 6. That tells us to round up. Whereas if it was a number between 0 and 4, you would not round up. So $4,049, don't forget your dollar sign, and 58 cents. Let's try another one. It says you deposited $4,800 into an account that pays 6.5% interest, annual interest compounded continuously. What happens after 3 years? So this time, 4,800 E to the 0.065. So again, if you're having trouble putting this into a decimal, I know it is a decimal, but it's a percent right now. It's a decimal, it's a percentage that has a decimal in it. We need to write this rate as a decimal, so that's where the 0.65 comes in. And then 3 years. Type this whole thing into the calculator. So 4,800, Shift LN, parentheses, 0.065 times 3. And that comes out to $5,833.49. And don't forget the dollar sign. So that's how simple some of these will be. Just deciding which one is it, grabbing a calculator once you've written the equation, and figuring out the answer. Now they can get a little bit trickier than this. This is how we did it the first way as well. The last two models we did the same thing, where what if we don't know how much we started off with, and instead you know how much you end up with. Because it says you deposited some money into an account 8 years ago, but we don't know how much. The bank paid 4% annual interest compounded continuously, so again, you know you're using this formula. But now it says you have $1,200 in the account today. So $1,200 is really my A value, not my P value. And it says how much money did you initially invest 8 years ago. Now instead of actually substituting $1,200 in for A, there's two ways to do this problem. You can still plug $1,200 in for P if you have a negative time, because you're going to say 8 years ago. So T we'll put in a -8 for. R is still 0.04. And then let's go ahead and plug the rest in and see what it comes out to. So 0.04 times -8. Okay, Okay, so this is what we type into the calculator. Now the answer we get should be less than 1,200 because this was 8 years ago that we put in a certain amount and we ended up with 1,200 when we were done. So 1,200, shift ln to get the e, parentheses 0.04, oops, times -8. And that comes out to $871.38 once you round that up again. That is the final answer. All right, and that's pretty much where we stop. At this point, you could have done this another way. Again, if you had plugged 1,200 in for A and solved for P, that would have been fine too. I think that tends to have more steps, so this feels a little bit quicker. But if you do have questions, I'll be back to answer them in just another day. All right, so if you do have any questions on these, just save them. Try your homework out as well, but this will also be posted on the website in case you need to see it again.